Okay, so before starting, I want to check. Yeah, I'm audible, I think, completely. So let me start the session by introducing myself. I am Oina Ghoshal. I am a PhD student at Indian Institute of Science Education and Research, Kolkata, and I have been assigned as the TA for this course, which is entitled as uh, Fundamentals of Spectroscopy, and which is which was taught actually by Professor Sayan Bakchi and Professor Anirban Hajra. And this is assignment regarding week number 11, where Professor Sayan Bakchi has explained some topics regarding ESI spectroscopy and only a single lecture about NMR spectroscopy because five lectures are already done in the previous week. So in this week, actually, what I'm going to show that in case of nuclear spin, which kind of spectroscopy happens and why it is relevant so much. So from the very beginning, we have started learning spectroscopy. That what is spectroscopy, why it is so much necessary, and then we have gone through a lot of spectroscopy techniques, namely rotational spectroscopy first, then vibrational spectroscopy, then we have gone to rotational vibrational spectroscopy, and then Raman spectroscopy. Next, we have moved to NMR spectroscopy, and today we are going to look at another spectroscopy technique, which is known as ESS spectroscopy. And next, on the next day, we will learn about electronic spectroscopy. So, to begin with, what we have discussed in the previous weeks, I am just going through that in a very short detail. So this is our discussion. This was actually we have discussed that in the previous couple of discussions we have discussed about resonance spectroscopy, and we have seen that two forms of spin could be possible: alpha spin and beta spin, and these two types of spin are also possible for as well as nucleus and electron. Okay. So for both electron and nucleus, these two types of spin states are possible, but the position of these two different spin states, position means in terms of energy, this position will differ. Okay. So for electron, that alpha state is higher in energy than the beta state, but for nucleus, it is the opposite case. That is, the alpha state is lower in energy and beta state is higher in energy. Okay, and then using this, we have stated that this nuclear spin is very much important when you are discussing about NMR spectroscopy. And then electron spin is much more important when we are actually dealing with electron spin resonance spectroscopy, that is ESR spectroscopy, which we will discuss today. So we have said that these alpha and beta spin states energy for electron and proton, and this is actually degenerate state. Okay. Initially, when there is no magnetic field, suppose B, if B denotes the magnetic field, B is actually 0 in the beginning. Okay. So when you are giving magnetic field from outside, that is B is not equal to 0, this degeneracy is uplifted. Okay. We have seen the same thing in case of Stark effect of rotational level. Okay. So it depends upon it is either alpha or beta, or this is beta or alpha. Okay. Depends upon whether you are considering nucleus or you are considering electron, right? So you have seen the same thing in case of rotational level. In case of rotational energy level, this is called Stark effect. The same thing it is happening for uh, the same thing is happening for magnetic field. In case of magnetic field, or in terms of resonance spectroscopy, I would say that in presence of magnetic field, these levels are actually splitting and the degeneracy is actually broken. Okay, so this is known as Zeeman effect. So I have said the difference between these two effects, Stark effect and Zeeman effect. That is rotational level. In case of Stark effect, electric field is necessary. This is splitting of this degeneracy in presence of electric field, and this is the splitting of degeneracy in presence of magnetic field. Then recording of NMR signal with fixed B and varying radio frequency, and also vice versa. Okay, this was also discussed that whenever going to uh, you are going to measure some NMR signal, then you know this formula. I'm writing it down here, that nu of radio frequency will be equals to, the formula is Gn beta n by h into b. Okay, so to measure this NMR signal, either you can vary this one fixing this b, or you can vary b by fixing this radio frequency. Okay, so by this way you can measure NMR. Either of these two ways are possible. And then there was a discussion on NMR inactivity of 12C and 16O. Okay, so for 12C and 16O, the case is that for these two system I equal to 0. Okay, so since I equal to 0, so this nuclei doesn't show any spin. That's why they are actually NMR inactive. So 12C is actually NMR inactive. Whenever, if you are, I don't know whether you have recorded in NMR or something, I don't know. But if you have recorded it, or if you are going to record it in future, then you can see that with proton there is an NMR of carbon NMR, and this carbon is C13, not C12. Why not C12? You know this fact right now, that 12 carbon is actually NMR inactive. So to become and to record the NMR signal, you need to have carbon 13. Okay. Next, we have discussed that why NMR experiments are done in presence of high magnetic field. Why? Because we have discussed that the ratio of alpha and beta state in alpha minus in beta. I am just writing the expression directly from previous day's discussion. If you cannot follow it, if you can see the previous day's discussion where I have discussed all these topics. That n alpha minus n beta is equals to Gn beta n into B by 2 kt. Yeah, this was the expression. N alpha minus n beta by B total, and also we have discussed that beta n, it is very small. So in alpha and in beta at room temperature they are almost equally populated. So population difference is very less because beta n is very low. So to make a transition, or to understand the spectroscopy, we need to have transition, right? From lower state there is would be a transition to the upper state. So for that you need a magnetic field higher in mellow, because if magnetic field is lower, this total value will be very low, and then n alpha and n beta will have almost equal magnitude, almost equal population. So if they are almost equal population, so there will be no transition. But to make some transition possible, you need to have some magnetic field which actually change the difference between the population of these two states. Okay. So that's why NMR experiments actually are done in presence of high magnetic field. Okay. Next, the two relaxation conditions were discussed. One is called longitudinal or spin lattice relaxation, and another is called spin relaxation or transverse relaxation. So we have discussed about that what these two means actually, and we have also discussed that the spin relaxation is actually responsible for the width of the NMR peak. Next, the selection rule was discussed that, and the main thing that was discussed is magnetic field due to circular motion of electrons would be perpendicular to the external magnetic field. That is, there is some electron which is moving, circulating. Okay, so they will create a magnetic field. And to be NMR active, the external magnetic field should be perpendicular to the magnetic field that is created by the movement of electron. And this creation of magnetic field actually, the magnetic field that was actually experiencing by the nuclei is was B initially, but the movement of electron actually creates some another magnetic field. Okay, so if now I name it Bl, and there is a constant it was introduced. This is called sigma, which is known as shielding constant. The shielding constant is actually because the magnetic field actually opposes the external magnetic field. Okay, so the magnetic field which is present there, they actually opposes it. So as magnetic field is increased due to the motion of electron, the motion of electron will create this magnetic field. So as the magnetic field is increased, So this will much more oppose the external magnetic field. So there, from there, sigma concept of shielding constant was taken, and then the change of the position of the peaks due to chemical dissimilarity, it was discussed that if all protons have if all protons follow the same rule, so they all the protons in a molecule, whether it is a large ring molecule or a small methyl group, so so all the protons would be resonating at the same position. But this is not the case. You also know that this is not actually the case. All the protons does not resonate at the same position. Why there is shift? Because they are of chemical dissimilarity. Okay. Then it was shown that for benzaldehyde, if you analyze the position for a benzaldehyde, suppose this is benzaldehyde, you know this. So these two protons are not same. Okay, and since this hydrogen is actually attached with the carbon, which is, so if I go through the structure of benzaldehyde, so this hydrogen is actually attached to a carbon which is attached to an electronegative atom of oxygen. So there will be less electron density around this, so this will be less shielded. That means if it is less shielded, then it will be going upward. So high, it will have high del value. So these two positions of this aldehyde hydrogen and methyl hydrogen, that was also discussed for benzaldehyde. Now there was some problem with this, because it was shown that if you change this magnetic field, there is a relation. I think I have this relation, which yeah, the relation actually was this thing, this B2 minus B1 by B2, which was almost equals to sigma 2 minus sigma 1. So if you change B1 or B2, then sigma 2 and sigma 1, that is the shift between these two hydrogens will shift. Suppose you are measuring this benzaldehyde thing, and you are measuring it with some difference, and if you change this B, that is the external magnetic field, then you see that your position will change. This will be very problematic. That's why the scientists took a solution, that they have considered using a substance which is called PMS, or trimethylsilane. This is called a standard substance because it is resonated as zero. Okay, and then all the other parameters that was measured with respect to this one. Okay, next, factors that affect the chemical shift. This was also discussed, that electronegativity and ring current are the two factors on which this is depends. Okay, so it was also very well discussed by Professor Shanbakshi, that how electronegativity actually affects the molecule. And today, even we will discuss, there will be something like related to this. Then I will discuss. And what is ring current, you have understood. I have give you detailed description. Suppose you have a double bond molecule, suppose C double bond C. So you suppose our benzene molecule, okay, I'm taking the example of benzene. This will be very much easy for everybody to understand it. Okay, so this is benzene. So what actually benzene is like this one, okay, this plan. And here is some electron density, and there is some electron density. So there will be a magnetic flux, that will be a motion of this electron, that will magnetic flux over there. Okay, so this will move like this, and it is shown if you are posing some magnetic field from there. So the proton which is present here, I am just changing the color so that you will be able to understand that. Yeah, so the proton which is present here, the proton which will present here doesn't have the same environment, right? These two will not have the same environment. Why? Because in this position, this B is aligned with this is perpendicular, so here B increases, and but here the magnetic field will oppose this B. So in this position, B decreases. So since here magnetic field is increased, that means this will be less shielded. Okay, and if in the upper position, In the upper position, the magnetic field is decreased, so this will be much more shielded. So since it is much more shielded, then it will be going to upfield. Okay. So the two hydrogens of benzene will not come in the same position. Okay. Now it was shown that what I've said, that NMR signal of different proton occurs at different position for aromatic molecules. And the splitting of the peaks in the high resolution NMR spectrum, which was also discussed in terms of Pascal's triangle. That which, how many peaks will be there, this was also discussed in terms of Pascal's triangle. Pascal's triangle can say that if there is a splitting, what should be the ratio of the intensity of the peaks, that you can get easily from Pascal's triangle idea. Then the characteristics of high resolution NMR spectra is also discussed, that fine structure they can be obtained due to spin-spin coupling. And then the calculation of the coupling constant, that was also discussed in terms of tree diagram like this, and this, the gap between these two, this is J, nothing but J. So this is called coupling constant. Okay. And then number of peaks, how many number of peaks would be observed, that was shown that for any molecule with I equal to half, this should be equal to n plus 1. But for a system with nuclear spin I, the total number of signals are given by 2ni plus 1. Okay. So this was also the discussion of the previous day's discussion, that I have given you a recapitulation. So with the discussion of uh, today's module, I am going to discuss a small discussion of yeah. Okay. Is there anybody? No. Okay. So I'm going to today's discussion, where I'll talk about only one question, only on one module from NMR spectroscopy, and then we'll move directly to ESS spectroscopy. Okay. So so far what we have discussed for NMR spectroscopy, then there is some validity of this n plus 1 rule. It was shown that any validity of this n plus 1 rule for I equal to half system. It was shown for I equal to half system only, this n plus 1 rule holds. Okay. Yeah. But for other system of where your I is not equal to 0, oh sorry, not equal to half, not equal to half. For that kind of system, the rule is 2ni plus 1. Okay. So if you have any query that why this is different, this is not different. Okay. So this is 2ni plus 1, and if you put I equals to half, then what will happen? This will be 2n into half plus 1. You can see that this will become n plus 1. That is the same rule. Okay. So this is more generalized rule, that 2n I plus 1 will be the number of fine structures. And then there was a discussion for the chemical shift of CH3 X type molecule. Okay, what is this kind of molecule? What is X? X actually refers to fluorine, chlorine, bromine, and iodine. F, Cl, Br, and I. Okay, so if you have suppose CH3F, if you have CH3Cl, CH3Br, and if you have CH3I, suppose. Okay. So among them, fluorine is much more electronegative. So it will take much electron density from carbon. So, okay. So carbon will be much more delta positive for fluoride phase. Okay. What I'm trying to say. So this is hydrogen, carbon, carbon, hydrogen. This is fluorine. Okay. Suppose. So yeah, this is fluorine. Okay. So since fluorine is much more electronegative, so it will pull electron density from carbon. Since it will pull electron density from carbon, so carbon will become much more delta plus character or electropositive. Okay. Since it will become much more electropositive, so these hydrogens will be, what will happen? For hydrogen, this will be less shielded. Okay. Since they will be less shielded, so its chemical shift will be higher. That means the delta of CH3F will be higher than delta of CH3Cl greater than delta of CH3Br and so on. So this is the order for and this is the order of chemical shift for CH3X kind of molecule. Okay, with how electronegativity change, how this chemical shift is changing, it is also shown. Now there was a discussion for the proof of presence of water in methanol using NMR spectroscopy. How that was proved? Achha, okay. So I'd like to take another empty space. Yeah, yeah. So methanol CH3OH, right? So how many kinds of proton are there? Suppose I'm writing two protons are there. This is CH3A. I think writing is A, and this is I'm writing B. Okay. So you can take the name of others. So 3A and 1B. Okay. So in the NMR, how many peak will be there? So this weight for A proton, how many peaks will be there? So A proton means this CH3. So according to n plus 1 rule, that there is only one hydrogen is over there. So this will be 2 peaks. Right? Now for B proton, what will happen? B proton means this CH3OH proton. So it has 3 hydrogens with carbon according to n plus 1 rule. So there will be 3 plus 1, that means 4 peaks. So the 2 peaks will be there. One is for A proton, another is for B proton. Okay. Now what should be the ratio for these 2 peaks? So this will be 1:1, and these 4 peaks. What about these 4 peaks? This will be 1:3:3:1. So if I am going to draw this in a spectrum, how it will look like? So this is your delta value. Okay. So now you have to find which of these will be higher in delta value. Okay, delta value increases from right to left. Always remember that for NMR case, this delta value is actually increasing from right to left. So what happens actually that this proton A, this is for CH3, okay, and this B proton is directly attached to oxygen, which is much more electronegative. So H will be delta of A much more, sorry, less than delta of B. Why? Because I have said that B, whichever is much more deshielded, this will be of higher delta. Okay. And if you can see for A and B proton is much more attached with oxygen. Since B proton is attached with oxygen, so the electronegativity of oxygen will pull the electron density from B proton, and then B proton will be much more in delta value. So there is 1:1 peak by 2, and ignore my poor drawing like this. Okay, this is terrible drawing. Yeah. So this ratio is 1:1, and this ratio is actually 1:3 is to 3 is to 1, right? So delta value will increase from right to left. Hmm? Which is for this one? This is HA, and what is this one? This one is HB. Cool. Okay. Now, if water is present, so what will happen if H2O is present? So what will be the effect? If water is present, if water is present, then what will happen? This water, this OH group will exchange proton with this one water. Okay, and since it will exchange protons with continue with a dynamic rate, then the if water is present, then four peaks of B will not be resolved. Okay, what does that mean? You cannot see these four indistinguishable peaks if water is present because it will continue exchange your proton. Okay, so this proton will not going to interact with oxygen, and you already see that low resolution spectrum. In low resolution, you cannot see just a B line. Okay, in low resolution you just see now only one line. But if you are seeing just one line, if you can see clearly, then you can see that on this one line is divided into four lines. Okay, so if water is present, this splitting will not be there, and you only see a low resolution spectrum like the thing. Okay. Yeah. And next, it was shown that for ethanol also CH2 proton interacts with both CH3 proton and OH proton. Okay. Now I'm going to the case of ethanol. Okay. So what is ethanol? You know, just I will sorry, use another color here. Now I am moving to ethanol. So similarly, just like methanol, I am just naming it. This is A CH2OH. This is B, suppose, and I am naming it as C. Okay. So here you can see how many splitting will be here for hydrogen. You can see its nearby neighbor will have two hydrogens. So 2 plus 1, there will be 3 peaks. What should be the ratio of these peaks? 1 is to 2 is to 1. Because you can know from Pascal's triangle, the ratio will be divided into this category. Okay. Okay. So for clarification, I am just writing Pascal's triangle. So this is 1, 1, 1. This one is again 1, 1 plus 2, 2. This is 1. So for three splitting, you can see 1 is to 2 is to 1 ratio. But for 4 1, you can see 1 3 3 1. So I have written that 1 3 3 1 there. So it is 1 is to 2 is to 1. Okay. Now I am going to HC. How should be the fate of HC? HC will be, there is two protons here, so it will be also 3 peaks. Okay. But if you are coming to this point, that for what happened to this CH2, there is three protons on the left, one proton on the right, so there will be four protons, and four protons will be there. That means there should be 4 plus 1, so 5 peaks will be there for CH2 p proton. That is not the case. Why that is not the case? Because these two protons are not equivalent. Okay, the two protons that is CH2 will interact, that are not equivalent. So this will completely depend upon which is much more coupling favored. Okay, this depends. The splitting depends. Oh, okay. So the ratio will be here same, 1 is to 2 is to 1. This depends upon J value. That means J of CH2OH and J of CH to CH3. So actually it actually depends on that CH2 group is actually interacting with this OH mode or CH3 mode. This this is the main factor becoming here. Okay. So actually it is seen that if so two cases are possible. The first case, suppose J of CH2OH it is much higher than J of CH2CH3. So what will happen? So first coupling will happen with this one OH. Okay. So these two will couple with these two. Okay. So there will be how much peaks? Two peaks. First two peaks will be there, and then these two peaks. So this is one. This will be in two peaks. Understand this clearly, then it will be very much beneficial. So first coupling with OH, since I am writing that coupling with OH is higher, so there will be two peaks. Okay, and then coupling with CH2 will happen, and these four peaks, these two peaks will be divided into four peaks. Okay, so total 8 peaks we will get if J of CH2OH is greater than J of CH2CH3. And if the opposite case happens that J of CH2OH much less than J of CH2CH3, okay. So initially coupling with CH2CH3 will happen, and initially we will get there is 3 protons, so you initially will get 4 peaks, and then coupling with CH2OH will happen, and each peak will divide it into 2 peaks. Another here also 8 peaks will be there, but this 8 peaks intensity will be different. This will be 1:3:3:1 intensity ratio distribution, and then there will follow 1:1 distribution. Okay, so the difference is that both contains 8 peaks, but this four here first 2 peaks observed, and these 2 peaks are divided into 4 peaks, that is giving you 8 peak. But here first 4 peaks are observed, which is dividing into 2 peaks, and you will get 8 peaks. But actually this is seen that this is the actual case. Okay, experimentally it is seen that this is the actual case. So if so using NMR you can easily detect if water is present or not. Why? Because if water is present and it exchange hydrogen with this one, okay, so water will change this exchange this hydrogen, right? So this coupling will be hampered, right? This hydrogen will the CH2 hydrogen will coupling to this OH bond, but if hydrogen is actually replaced, then this coupling will be hampered, right? But actually what I have said that in practice it is shown that CH2 is mainly coupling with CH3. So if water is present in this car, this is exchange is taking place, then you will not see any change in the NMR spectrum. Okay, which you also confirms you that the coupling is mainly happening with CH3, right? Because if coupling is mainly happening with OH, if that will be the case that OH is coupling more, then you will see that at as in presence of water, the exchange of water hydrogen will take place. But this is not the case. Okay, and then you have shown that for HD molecule, that taking one HNMR or DNMR gives different number of peaks, but the difference between the peaks is same, which is nothing but J. Yeah, for HD molecule, what is this is what I am going to say that for hydrogen NMR, suppose hydrogen NMR will give how many peaks? 2 into means 1 into half plus 1. So that will be 2 peaks. So if you're going through deuterium NMR, so if you're going through deuterium NMR, which has I equals to 1, so 2 into 1 into 1 plus 1, which will be 3 peaks. Okay, so if you are getting taking hydrogen NMR, then you will see two peaks, and if you are getting deuterium NMR, you will get three peaks. But the difference between the peaks will be always same. Okay, this will be J. So this was the discussion up to which NMR spectroscopy was discussed by Professor San Bakchi. Now I am going to new spectroscopic technique which I have mentioned the name, nothing but ESR spectroscopy or EPR spectroscopy. So EPR actually is shown by the species which has one or more unpaired electron. This is the foremost condition and very important condition to show ESR activity, that this molecule must have one or more unpaired electron. And this has application in predicting organic reaction mechanism that involve free radical, because free radical means there will be unpaired electron always. Okay. So there will be always unpaired some unpaired electron will be there. So since free radicals involve some unpaired electron, that means for any organic reaction which is going through suppose free radical mechanism, and in free radical there is unpaired electron, so you will get some signal in the ESS. So if with us with an intermediate compound, if you are going through ESS spectroscopy and if you get some signal, you will say that the yes free radical is actually forming. Now there is a discussion that the intensity of the peak actually depends upon the concentration of the free radical. Okay, yeah, it is actually depends upon concentration of free radical or paramagnetic compound. Okay, so what is the concentration upon which the peak's intensity will vary? Also, the sensitivity is important for here in this case, and it is sensitive up to, that was mentioned as 10 to the power minus 3 mole. Okay, minus 13 mole. And also, this was the width of the peak, width of the peak. This is depends upon delta nu, which is 1 by 2 pi tau. And you know this spin relaxation is actually happening in some 100 nanosecond scale. If you put it here, you can see this new delta nu will be nearly equals to 1 megahertz. So peak is very much broad. And which on which factor this peak width is dependent? This peak width is actually dependent on the relaxation time, or what is written here as tau. Okay. Now there was a discussion that there is some advantage of EPR and there is some disadvantage of EPR. Okay. What is the advantage? That homogeneity of magnetic field is less critical because this is, energy gap is very high. Okay, yeah, this is advantageous because uh, the homogeneity of magnetic field is not required everywhere. But the disadvantage is that, main disadvantage is that peak location means it is a broad spectrum. Suppose this time, okay, so the which one is the peak? This one, this one, this one, this one, or this one, you cannot detect. That's why a differential plot is done, and it is shown that, and you know that in with your knowledge of mathematics, that at maxima or minima first derivative becomes zero. So if you have to doing a differential plot, here you see, here the slope is positive, there the slope is negative. Okay, but here that is the extreme point where the slope is zero, actually zero. Okay, so here you can see there is a zero. So if you take this differential plot, and in the zero position will be actually your maxima, you will get the maxima from here, right? Okay, and then there was discussion of experimental and theoretical basis of G factor. Generally, in experiment, the G factor comes with in the theory, G factor of electron was discussed as G equal to 2.002. If I am right, yeah. And experimentally, this is the theoretical prediction. And experimental prediction tells that the G value is actually between 2.002 plus minus 0.003. Okay, so this is the range of G value actually you are getting experimentally. Why that is so different? Because experimentally spin orbit coupling factor actually arises. Okay, and since spin orbit, when there is a spin orbit, generally here you can see another G value on sometimes other than this one. this is actually considering no spin orbit coupling. There is no spin orbit coupling, so you will get the value of 2.002. If for transition metal, whenever there is a chance of spin orbit coupling, you can see that the G factor is actually changed, okay, and the spin orbit coupling factor actually introduces there, and the G is given by some equation which is given as G is equals to, I'm writing the equation, 1 plus J into J plus 1 minus L into L plus 1 plus S into S plus 1 by 2 J into J plus 1. So you can see here the expression of G, whenever there is some spin orbit coupling in the system, G will take this form, okay, and this G is known as Landis G factor. Okay, so this G is actually called Landis G factor. Okay, so this is the discussion of lecture number 53, where Professor Sanbakshi has discussed about Landis G factor. But there next in the next lecture there was some discussion that for hydrogen atom it is only one line is expected because only one electron is present, but it shows two lines experimentally. Why this is showing two lines? This was the first question, that here only one line is expected but it's showing two lines. Okay, why two lines is expected? Because it is said that there the electron can interact with the nucleus. Which electron will interact with the nucleus? All the electrons interact with the nucleus? No, the electron of in presence in the s orbital actually interact with the nucleus. Okay, and p orbital, other orbitals electron does not interact, because why they are not interacting? Because for s orbital the wave function psi of s is not equal to 0 at the nucleus. Okay, if you see the structure of s is actually spherically symmetric, so at the very origin that the s has a significant value, but for p you can see p or d there is some node there, so wave function is 0. So that's why s electrons present in the s orbital actually interact with the nucleus. So for hydrogen, which has electronic configuration of 1s1, this one electron which is present in s actually interact with with the nucleus, and you know for hydrogen nucleus I equals to half. Okay, so since I equal to half, two mi value are possible. Mi equal to plus half, or it could be mi equal to minus half, right? So these two I values are possible actually. And this gives rise to actually which is called hyperfine interaction. Yeah, so this is actually known as hyperfine interaction. Okay, and for that another constant is introduced which is known as A, which is for hyperfine coupling constant, which actually measures how strongly a coupling between the electron of the s orbital and nucleus is happening. Okay, and for hydrogen it was shown that, I am just writing all the energies, it was also discussed by Professor Sanbakshi that the interaction energy can be written like this: E equal to A mi ms h, right? So this was actually your transition initially. This is from alpha state, this is for beta. Yeah. Okay, so it is better that if I can take another slide. So this is a very interesting period which I want to discuss. Yeah. Yeah. So in absence of magnetic field, so I am writing this E value. E is nothing but A ms mi h h. Yeah. So when B is equals to 0, this alpha and beta spin states are identical. But whenever there is some magnetic field, this degeneracy is broken and two states are generated. One is alpha state, another is beta state. Okay. And for nucleus, if you can remember, sorry, for electron, if you can remember, beta state of lower energy, alpha state of higher energy, right? Okay. And alpha sub so of alpha state, that is ms equals to plus half, and for beta state the ms is nothing but minus half. Now there is b is not equal to 0. Okay, this is beta and this is b is magnetic field. Okay, next when the hyperfine interaction is there, so hyperfine interaction is there, so it is saying that here hyperfine interaction, two states are formed. Okay, so there is some state here, there is some state, because it will interact with two mi values. Okay, so mi equals to, this is plus half, this is mi equals to minus half, and here similarly mi equals to plus half or mi equals to minus half. Okay, so four states are possible. So what should be the energy? Energy of beta state, actually initially it was I half gs beta and b. This was initially the energy, but now since hyperfine term is interested, so just rubbing it and writing it down. So hyperfine splitting. Okay, so this was the initial energy gs beta b. Now this energy term will also introduce, and now if for this state, suppose for this state, what is the value of ms? Minus half, right? What is the value of mi? This is plus half. So minus half, sorry, mi minus half, and h will be there. So 1 1 4, so half of this will be 4, so this will give plus h by 4. Okay, and here the similar thing will happen, since one is plus one is minus, so it will be minus h by 4. Okay, but you see here what happens, that this is of lower energy, right, and this is of higher energy, so the state will be just opposite. Okay, so your lower state will be of higher energy. Initially it was degenerate state, so that is so the differentiation is very much difficult. So this will be plus 1 and this will be plus 1. Understand this? And then similar case is happening here, that whenever I am taking minus half in the lower case, the energy will be minus half gs beta a beta b minus h by 4, and here the energy will be minus half gs beta b plus h by 4. How I'm getting plus and minus these values? Because I'm just calculating for one. Suppose E is equals to a ms mh mi and h. Okay, so for a into ms for plus half, suppose for I'm calculating for the top one. Okay, ms equals to, what is the value of ms? Ms is plus half, right? And what is the value of mi? Mi is also plus half, so I'm just putting this, and then h. So what we will get? H by 4 with positive sign. So that's how I am writing here. Okay. So four energy levels are there. So many kinds of transitions are possible. What I have said you earlier, that many lines possible for hydrogen. Yes, okay, many lines could be possible for hydrogen, but actually in practice, what happens? Two lines are observed. Why? Because there comes another important thing which you have forgotten, I think, but which is known as selection rule. Okay, this is very much important for spectroscopy. Selection rule. So what selection rule says? Selection rule says that only transitions are possible for which delta mi is 0. These transitions are only possible. That means from plus half mi, for mi equal to plus half, you can go to only mi equal to plus half. You cannot go to mi equal to minus half. So you can see here this transition is possible for, yeah, and for this transition is possible. So that's why you see two lines in the spectrum. Okay, and what should be the difference between energy? Okay, so for this, for mi half plus half to mi equal to minus half plus half to plus half, what is the change in energy? Change in energy is gs beta b. Suppose, yeah, so plus h by 4 plus h by 4 to 2h by 4. Okay, and what will be the change in energy for, suppose for this is for nu 1, this is for nu 2, and what would be the value of nu 2? Nu 2 should be equals to same gs beta b plus gs beta b minus 2ah by 4. Okay, so I am just minus from this one to this to this. Okay, highest to minus lower. So what should the difference? Nu 1 minus nu 2. Just put these values, this gs will cancel, so we'll get 2ah by 4 plus 2ah by 4, because there is a minus, so if you just subtract it, it will become plus. So 4ah by 4. Okay, so h. Okay, so this is actually in terms of energy. This is actually in terms of energy. If you can just convert this energy to h nu, just h will cancel, you can see that delta nu will be a. That means the separation between the peaks is the hyperfine splitting constant. Okay, so what I'm just trying to say that this hyperfine splitting constant is nothing but the separation between the two peaks. Got it? Okay, so in the next lecture of lecture 55, the hyperfine splitting was also obtained using T diagram. Okay, so how many ways they will be divided, because you have learned this T diagram, so I'm not just expressing this here. And for D atom for which ID equals to 1, 3 MIs are possible, and all of which, so this for D equals to 1, ID equals to 1 for deuterium, so 3 MI values are possible, and for 3 MI values, the separation, suppose here is plus minus 1, mi equals to minus 1, here is 0, and here is plus 1. So the separation is actually value of a. Separation is actually nothing but a. Okay, and also there is a discussion of ESR spectra for CH3 radical, which is very much important, and it was shown just like hydrogen, that's what I have shown, 4 lines in the ESR spectra. Okay, for CH3 radical, why 4 lines are obtained? Because you can see there will be ms value of plus half, minus half. Okay, so 4 lines corresponds to each one, and then uh, for 3 hydrogen there will be, you can see for 3 hydrogen the 8 combinations are possible, 2 different ways. By 2 different ways, Professor Sandberg has explained that. You can see this lecture and also find in lecture number 55. And also why 4 transitions are possible in this case? Because you can see the selection rule. What I have said here, that delta mi should be equals to 0. That is, the transition will be from the mi state to another mi state with the same value. Okay, and then in the lecture number 56, hyperfine coupling constant A is related to hyper unpaired electron density. So it was shown that A is proportional to rho. So I can write this A as A equal to R into rho. Okay, so and this R you can calculate as A by rho. That's the simple mathematics, right? Now for methyl radical, I'm going to the next page. For CH3 radical, A equals to 0.05 Tesla. Okay, sorry, I'm just putting value of hydrogen. So A is 23 millitesla. Okay, and I can write in terms of Tesla as 23 into 10 to the minus 3. And the rho, you can have to find this rho with the known value of R. R is nothing but 0.5 Tesla. So if you are finding rho, you will find this rho is value is 0.046. Okay. So if total value is 1, then remaining portion is 1 minus 0.05. Okay. So okay, so only one proton I am just counting it. So yeah. So for electron density for one proton, it is given as 0.046. Now for CH3 dot radical, you know there is 3 protons. So what should be the intensity? 0.046 into 3. This will come 0.138. Okay, so approximately 0.14. So you can see this 14%. If total rho is 1, you can see that 14% of electron density of this unpaired electron is resides on this hydrogen. So main the 80 remaining 86% is 14% time it resides on hydrogen, and 86% time is 6. 86% time it resides on carbon. Okay, so whatever I have said you, I have written it that cis radicals home, it can be shown that the unpaired electron resides 14% time on hydrogen and remaining 86% time on carbon. And then the geometry was discussed, that which one could be the geometry for this radical. Yeah, so two geometries were predicted. This is called planar geometry. Here three hydrogens are in the same plane, and this is p orbital which is perpendicular. Another predicted experiment is three hydrogens are there, and this lone pair will be in the sp3 orbital. Okay, so which could be the most probable structure? So you can see that this is pure p, right? This is pure p, and this is sp3, and this has s character of 25%. Since there is 25% s character, so you can see that this electron will much more you get s character in this pyramidal geometry, right? So this is pyramidal geometry, and this is planar geometry. Okay, so electron will much more reside on this ch3, right? And since this is a pyramidal geometry and this s character is involved, that means if in the ESS signal you can see a splitting or hyperfine splitting due to this s electron, splitting due to s electron is possible, then you can say that this is the structure. And but if there is no splitting or very less splitting, you can say that this s electron is not involved and this is purely p character. The electron, which is the unpaired electron is residing in an orbital which is very much less of s character, but that means it is more p character. Okay, in the expression, in the when you are taking the APR of methyl radical, it is generally seen that there is less hyperfine splitting, which actually suggested this structure, this planar structure, because less hyperfine splitting means there is very much less of hyperfine splitting, means there is very much less coupling between electron and nucleus. That means more preferred geometry is the planar geometry. And also, oh yeah, so I one thing I have mentioned, but I forgot. So for this, to check this coupling, you cannot check this coupling with 12C, right? Because 12C is inactive, just like I equal to 0, so it will not be used. So you have to take 13C, and then 13C will take you splitting. Okay. Now, if different nuclei are present, then number of hyperfine lines will be given by this expression pi of I into 2ni plus 1. So, if the expression was there 2ni plus 1, that you need to multiply for each case. Okay, and then calculating the number of hyperfine lines for CH2Cl and CH3Cl2. Okay, so this was also discussed. Professor Sandberg has calculated. So if you have not calculated, you just calculate it and then the check with the answer what I am writing here right now. Fine. Yeah. So for CH2Cl, actually the case is that for CH2Cl in the hyperfine splitting structure, you can see total 12 peaks. And for CAG, CA13C, HD2, in this case, since 13C is there, the coupling between is possible, and you will see total 20 peaks. You just check it using this formula, and I am also going to do mathematics regarding this. So this was all the discussion about ESR spectroscopy that Professor Sandberg has discussed. Now I am moving to some questions regarding ESR spectroscopy. Yeah. So, first question is the high resolution proton NMR spectrum of CH3 CH2Cl has 4 fine structure for CH3 proton and 3 fine structure for CH2 proton, or 3 fine structure for CH3 proton, 4 fine structure for CH2. CH2 protons are observed as a higher D than the CH3, and CH2 protons are observed as a higher D than CH3. So you can find this answer in lecture number 51 where there was a discussion on how many signals will be there in the NMR. So this is the discussion I have written here for your easily understanding. I'm just reading it. And green one will be helpful. Yeah. So for a proton NMR of CH3 CH2Cl, the CH3 proton will couple with neighboring 2 protons of CH2, right? Because I'm just writing it. So whenever you are just measuring this one, suppose this is HA, this is of HB, 2 types of protons are there. So it will couple with the neighboring one, okay? These 2 protons. So this will give 2 plus 1, n plus 1 rule. Remember, guys, that n plus 1 rule is valid here because I is half for hydrogen, okay? So if I is not half, then if suppose there is CDCA, CD3, CD2Cl, your n will be not equal to 1. Then you have to use this 2ni plus 1 formula. So 3 peaks will be there. For CH2, there is 3 hydrogens, so you will get for B proton there will be 3 plus 1, so 4 peaks. So that is the thing I have written here. In the high resolution NMR spectrum, there will be 3 peaks. In the high resolution NMR spectrum, following n plus 1 rule. Similarly, CH2 protons, they actually couple with 3 protons of CH3, therefore giving 4 peaks. Okay. So the first answer you got that 3 peaks for CH3 proton and 4 fine structure for hydrogen CH2 proton. This is correct one. Okay. Now you have to prove that which should we have higher shifted. Okay. So I have said that higher. Now I am going by backward from backward. Higher value of D or delta, whichever is possible. Higher value of D. That means delta is increasing. Okay. So higher value of delta means this one, this one. Suppose I am naming it at AB I have used. So XY. Suppose I am writing it at XY. Suppose this is X, this is Y. Okay. So which one is higher in del value? X. Because in from left to right, this is increasing. Okay. So if X is higher in del value, that means it is uphill shifted. So higher value of delta means uphill shift. And you know, whenever I have discussed this NMR, uphill shift is happens if the proton is less shielded. If the proton is less shielded, right? So higher value of delta, that means upfield shift of this proton signal, which means it is very much less shielded. Okay. Now from less shielded, you can guess which proton is this less electron density. Okay, high electron density means there will be a movement of electrons, so they will create magnetic field, they will shield more, right? So less shielding means there will be less electron density, right? Now we have to find among CH3 and CH2 which will have less electron density. You can see that CH2, this B1 is attached to directly chlorine. Okay, so since this is attached to chlorine, so its electron density will be B greater than A. Okay, because electron density is very much sorry, which will have higher electron density because proton is electronegative. So electron density B will be more in A, and in B electron density will be less. So I have to find less electron density. Which one has less electron density among these two? So I can see B has less electron density. That means B will be less shielded. That means B will have upfield shift. That means B will have higher del value. And you know which one is B? B is nothing but CH2 proton. So CH2 proton is actually observed at a higher del value. Okay. So this is the true options. I am correct that 3 fine structures for CH3 proton, 4 fine structures for CH2 protons, and also CH2 protons are observed at a higher d value than the CH2 proton. Got it? I'm moving to the next question, that if we compare the high resolution proton NMR spectrum of CH3, CH2, Cl and CH3, CHCl2, so will be there be a difference in the fine structure of CH3 proton, or they will be same? You can also find this in lecture number 51. Just I am just writing again the same thing, that for proton NMR of CH3, CH2, Cl, for CH3, okay, I'm writing below it. Yeah. So for CH3, CH2, Cl. Okay. For this case, suppose CH3, CH2, Cl. So I'm just interested in this CH3, and you can see there is two protons, so there will be three peaks. But CH3, CHCl2, here two Cls are there, but for coupling with the CH, there is only one proton present here. So two peaks are there. So actually, what happens for CH3Cl, CH2Cl and CH3CHCl2, that if you get this high resolution spectrum for CH3, you will see three peaks, but for CH3CHCl2, you will see only two peaks. So number of fine structure for CH3 proton are not same in both the molecules. Okay, and this is the answer. That the fine structure, number fine structure of CH3 protons are different because for CH3 CH2 Cl, three peaks can be possible, but for the CH3 CHCl2, only two peaks are possible. Okay, so I am moving to the next question. A free radical mechanism can be probed by using IR, NMR, microwave, and none of the above. So I have discussed it in lecture number 53. IR spectroscopy actually deals with vibration. Vibration. Okay. NMR spectroscopy actually deal with nuclear spin. Microwave spectroscopy is actually dealing with rotational level. So you can see here that the three spectroscopy techniques of all use, that IR is responsible for vibrational transition, NMR for nuclear spin, microwave for uh, rotational case. Sorry, rotational case. Okay. So whether in a compound there is an unpaired electron or not, This three, you can see this three is not affected. Okay. So the only thing that will be affected is the presence of unpaired electron. Some reaction is going through a free radical mechanism. That means what that will actually means? That actually means there is the presence of some unpaired electron. Okay, presence of some unpaired electron, and this unpaired electron I have also discussed that you can prove this using ESR only. So all of these above techniques, what I have written, that IS spectroscopy, NMR spectroscopy, microspectroscopy, these all are irrelevant when you are just going to find free radical in the reaction. Okay, so you need ESR spectroscopy's help from this one. So all of the free radical mechanism actually involves unpaired electron, which is actually possible to monitor using electron spin resonance or ESR spectroscopy. So the answer is none of the above. Okay. Number fourth question. The weights of the ESR peak actually depends on which one? Relaxation time of the spin states, the strength of the magnetic field, the number of unpaired electrons, and the concentration of the sample. So this is a question, very interesting question, and you can find this answer also in lecture number 53. That ESR spectroscopy gives generally broad signal. How you can get this broad signal? Because whenever I was discussing and in lecture number 53 content that ESR spectroscopy, what is the intensity ratio of the peaks of ESR spectroscopy. So intensity actually depends upon the concentration of sample. So weight will not be dependent upon the concentration. Okay. Also number of unpaired electrons, this will also depends this intensity, but the strength of magnetic field and relaxation time of the spin state, these two are main parameters. Okay, so each actually depends on the relaxation time. How this is depending? So width of a peak, or whenever you are taking a spectra, width is actually represented in terms of FWHM, that is known as full width at half maximum. Okay, so this is a maximum. This is also discussed in the very first of second class. This is the maximum, this is half position, and this is half position. This weight is called FWHM. Okay, and this weight is can be determined using this relation 2 pi tau. Okay, now this relaxation actually, this relaxation of the electronic states actually happens in the time scale of few hundred nanoseconds. Okay, so tau generally have value of few hundred nanosecond. Suppose I am taking all as an example as 100 nanosecond. Okay, so since tau is 100 nanosecond, so I am writing this 100 into 10 to the minus 9 second. So you will get 10 to the power minus 7 second. Okay, you just put this value of tau in this equation. So delta nu 1 by 2 pi into 10 to the power minus 7. So it will give almost uh, 10 to the power 6 hertz. That means it will be almost 1 megahertz. Okay, so you will get some value, but I am for clarification I am just taking the nearest one. So it will come nearly 1 megahertz. So you can imagine that an ESS spectra is something that have some spectra separation which is in terms of some megahertz. Okay, so the peaks will be much broader, and this peak, the broadening will depend upon tau. Lesser the relaxation time, more is the FWHM, or more is the broadening. Okay, so it will depends upon the relaxation time of the spin state. So this is the answer. Okay, so this is fourth question I am solved. Um, I'm just coming. 1 second. Okay, so sorry for this. Sorry. Okay, so I'm moving to the next question, which is, yeah, which of the following will show ESR signal? Is hydrogen, oxygen, carbon, and NO. This is a very interesting question. You will find whenever you will go, you will find some question regarding this, that which of the following will show ESR signal. Mainly, what you need to find, you need to actually find that which one of these have unpaired electron, right? So ESR activity is mainly governed by the presence of unpaired electron. Okay, so if there is unpaired electron, then it will show always ESR signal. So you will find this answer in lecture number 53. But I am going one by one, and I have all the MOs of these compounds. Then you will be able to understand that this is whether this will show is a signal or not. First, I am moving with the molecular orbital diagram of hydrogen. Okay. If you don't know how this molecular orbital, what is molecular orbital diagram, how this is coming, then you should learn this, and you will see that these two molecular orbitals are coming from two hydrogen atom. This will mix up, and there will be two orbital active. This is called bonding MO, and this is called anti-bonding MO. And this, you can see there is a pairing up of electron, and there is no electron. So there is no unpaired electron. Okay, so in this case, you can see there is no unpaired electron. No, so now I am moving to the next case. You can see this molecular orbital diagram of oxygen. Okay. Similarly, this is how this is coming. All these things you can see this in name of, which is not in the scope uh, of this course. So if for oxygen, you can see there is two unpaired electrons. So two unpaired electrons. Okay. So since I missed this. So no unpaired electron for hydrogen molecule. So you can see that hydrogen molecule will not show any ESR signal, but oxygen will have two unpaired electrons. So it will show a signal in the ESR spectroscopy. Okay. Now I am going to carbon. Carbon, you can see in this case there is no unpaired electron for singlet carbon, but for triplet carbon there is unpaired electron. So in general, carbon you will see always ESR signal. So this will be ESR active because unpaired electron. Okay. The fourth one is NO. So this is a complicated system. But have read that you can understand that NO system is a complicated system for which you can see that there is one unpaired electron here. Okay, and this unpaired electron is responsible for two any properties. So this unpaired electron needs it one unpaired electron. That means it will be ESR active. So you can see the three options are there which will be ESR active. Oxygen is active, carbon is active, and NO is also active. Okay, but for hydrogen there is no unpaired electron, so hydrogen will be ESR inactive. So answer is only oxygen, carbon, and NO. So moving to the next question, which of the following is correct for ESR? This is a statement-based question. You have known that you have also find in lecture number 53 that for ESR the energy levels are given as E alpha is given as minus half Gs beta into B, and beta is nothing but half Gs beta into B. Okay. So these two are expression for alpha and beta state. Fine. Now, what is the difference of energy? Delta E And first you need to know which one is of higher energy. Then you will find that what is the difference of energy. So for this, information is provided that beta is negative. For electron, beta is negative. But if it were the case of nucleus, then you will see that beta is positive. But here, since beta is negative, so since beta is negative, so this term is negative and this term is positive. Okay. So here the ground state is alpha, E alpha. Oh, sorry, ground state will be beta and higher state will be E alpha. E beta will have energy of half Gs beta into B, and the alpha will have energy minus of Gs beta into B. Okay, so these two thing is very important for E beta and E alpha, and if what should be the energy difference. Now, if delta E I am going to calculate, my energy difference will be E alpha minus E beta. Okay, so minus half minus Gs beta B. We'll see that. Okay. So half half will give it 1, and there is a minus sign because alpha is negative, and since beta is negative, so this part will be positive. So in this way, for delta E, in terms of mode value, we will see this value is Gs, beta, and P. Okay, so these varies the value of delta E. Now here beta is negative, and also one thing is very important here for the electronic case, that beta is very large. That means the energy difference between these two levels, that is the alpha and the beta, that is very large. Okay, since that is very large, so it will actually comes in the microwave region. Okay, so whenever you want to probe some some electrons from beta state to alpha state, you just need to use microwave radiation. Okay, so in this question, the frequency of ESR corresponds to microwave frequency. This is the correct answer. This is not the radio frequency. And if there is a question that in which case you use radio frequency is only used in case of NMR. Okay, and here also beta is negative. Okay, so these two are answers. So I'm moving to the next question. The seventh question: the electron in which of the orbital can interact with the nucleus? So it is already discussed. I have discussed this question. That in also you can also find it in lecture number 54. That the wave function of s orbital is actually non-zero. Sorry, s orbital is actually non-zero at the nucleus. Okay, so at nucleus, the wave function of s orbital is non-zero, but pd orbital, f orbital, they have a node at the nucleus, hence wave function is 0. Okay, so for basic clarity, I'm just drawing. This is s orbital, right? Now I'm going to draw some p orbital. This is p orbital. Okay, so since this is s orbital, you can see here in this area s is not 0. The wave function for s orbital is non-zero, right? But in this area, you can see that the p orbit in this area, this is c0. Okay, wave function is 0. Similarly, if I am going to draw this d orbital, you can see also that ah, suppose this is a d orbital, and you will also see that in the nucleus, this portion, this is actually 0. Okay, so any orbital pd orbital, their wave function is 0 and near the nucleus, but s orbital is spherical symmetric and it will have no 0 wave function in the nucleus. So this s orbital electron in this orbital actually interact with the nucleus, with the nucleus spin. Okay. So this s orbital electron actually interacts with the nuclear spin. So in the hyperfine structure, the mainly responsible orbital is s orbital. Okay. So next question, that ESR spectrum of a CH3 radical has how much will be the first you need to find that in I have given you this lecture in our 55, the CH3 radical. So what, how many number of lines will be there? 2ni plus 1, right? And C, since C is C12, nothing is mentioned, means it is C12 and it is inactive. E is an inactive, so it will not interact with the lone pair, with the unpaired electron. But these hydrogens will interact, and this will give 2 into n means 3 hydrogens are there, 3 into I is half for hydrogen plus 1. So this will kill cancel and this will give you 4 peaks. Okay. So 4 peaks will be there for CH3 radical in the ESR spectrum. Now you need to find what should be the ratio. So you can find this from Pascal's triangle, that this is 1 1, from this 1 2 1. This is for 3 peaks and this is for 4 peaks. 1 3 3. This is again 1. You can see the ratio is 1 is to ratio is 1 is to 3 is to 3 is to 1. Okay, so from Pascal's triangle, you can get the ratio of these 4 peaks, or intensity of these 4 peaks, which will be showing at 1 is to 3 is to 3 is to 1. That is written here. The 3 protons will have nuclear spin of half. 3 protons will be there of nuclear spin half. So I equal to half. So total number of peaks are given by 2ni plus 1. So 2 into 3 into half plus 1, that will be 4. So intensity ratio will follow the T diagram, and 4 hyperfine lines will, the intensity ratio 1 is to 3 is to 3 is to 1 will be obtained. So answer is 4 hyperfine lines with the intensity ratio 1 is to 3 is to 3 is to 1. Okay. So number of hyperfine lines in CH2D. Okay. So I am going to do that. You also find in lecture number 56. So CH2D. Next one, in the same question is there. So I am going to just do this and I will explain that. Next question. Okay. So you can see for CH2D, this lone pair will interact with hydrogen and also it will interact with deuterium. Okay. So whenever this type of questions is there, you see it can interact with carbon, interact with hydrogen. This electron can also interact. There is a very large chance that it can interact with deuterium. Okay. But for interaction with hydrogen carbon is not possible. Why? Because carbon is EPR silent. Okay, it does not show EPR signal. But interaction with hydrogen is possible and interaction with deuterium is possible. So hydrogen has I equals to half. So hydrogen has I equals to half, and deuterium has I equals to 1. Okay. So two nuclei are there. Two nuclei here. This electron will couple with, and these two nuclei, there is a common thing that this two will not have the same spin. Sorry, same nuclear spin. Okay. So what will happen actually, that you need to follow this formula which was written earlier, that the total number of lines will be gamma of I into 2ni ii plus 1. Okay. So for hydrogen, I am just writing 2 into how many hydrogens are there? 2 hydrogens. Into I of hydrogen is half plus 1 into 2 into how many deuteriums are there? Deuterium 1. What is the interaction? What is the nucleus spin of deuterium? This is also 1. This is 1. You can see this here is 3. Here is also 3. So you will get 9 peaks. Okay. So 9 is the answer. You understand this? Very simple math. This type of math generally come for ESR spectroscopy. You should be aware of that. In the next question, the same type of question is here, but whatever I'm going to do, I'm not going to include I'm not going to include this carbon, okay? Because I know for carbon this is not possible. For interaction with H, and there could be interaction with Cl, okay? So if there is interaction with hydrogen which has spin of half, and for chlorine the spin is 3 by 2, okay? Now you can find this in also lecture number 52, 56, and we will use you can see here there's two different nuclei are there, so we'll use the same formula, gamma I of 2 NiIi plus 1 rule, okay? So you would be 2 into how many of proton is there? Proton is only 2 there. What is the uh, nuclear spin? Half. No, what is the nuclear spin? Half, okay? And for the next part, for chlorine, how many chlorine is there? Only one chlorine. What is the spin? 3 by 2. So here this will come 3, and from next one it will come 4. This is 12. So this part is for hydrogen, and this part is for chlorine. This whole part, okay? So you will get 12 pixels there, okay? So this is just done. I have done this. That I have Cl is 3 by 2, I have hydrogen is half. So if there is a map, these high values will be provided to you. You will be able to then evaluate that what should be the number of lines that will be possible. So your answer is 12. Okay. So this is the discussion of ESR spectroscopy and some problems regarding ESR spectroscopy. I have also discussed that for hydrogen atom, why there are number of lines expected, but you only get you only get all the what is it? You only get double line, okay? So more lines are possible, but you only get two lines because of selection rule. That I have discussed, and for different nuclei environment, how many number of peaks will be there. I have also discussed, and why EISR is taken in a differential form or different derivative form. So I have also discussed that. Okay. So this is the discussion of ESR spectroscopy. This is also done. And in the earlier cases we have done in MR spectroscopy, so there was the discussion over resonance spectroscopy techniques, two resonance spectroscopy, that is nuclear and electronic resonance. These are also done. The next class, this will be the last class, and I will discuss about the electronic spectroscopy, and some questions I will solve again, some questions regarding electronic spectroscopy. So if you I will upload in this video in the YouTube, and if you find this any question, or if you have any doubt, you just tell me. Okay. So I am just stopping the recording, and the session is over now.